In this video, I want to talk about diagonalization of a matrix. And to start with, I need to talk about the idea of similar matrices. If I have two matrices A and B, I say A is similar to B. If A is equal to P, B P inverse for some invertible matrix P. And so when we want to diagonalize a matrix, the idea is now we want some D to be diagonal. So this is a diagonal matrix. And what we're trying to find is a diagonal matrix such that A is similar to the diagonal. So A is P, D, P inverse. And this is what it means to diagonalize a matrix. So we have a matrix and we want to write it so that it's similar to a diagonal matrix. When we do this, we're looking for two things, a matrix P and a matrix D. In order to find the matrix P, the columns are going to be linearly independent eigenvectors of A. So we can find all of the eigenvectors and write them as columns of the matrix, and this will be our matrix P. For the diagonal matrix D, the diagonal entries are the corresponding eigenvalues. So our eigenvalues give us our diagonal matrix and our eigenvectors give us our matrix P. So let's look at an example. Let's look at this matrix 1, 3, 4, 2. And we want to start with finding our eigenvalues. In order to do that, we subtract lambda from the diagonal. So I have 1 minus lambda, 3, 4, and 2 minus lambda. And we want to take this determinant. 1 minus lambda times 2 minus lambda, minus 12. And this needs to be equal to 0. Multiplying this out gives us lambda squared, minus 3 lambda, minus 10 equal to 0. We can factor this into lambda minus 5, lambda plus 2 equal to 0. So my eigenvalues are 5 and negative 2. So I'm going to write these up here. And now we need to find the eigenvectors. Let's start with lambda equal to 5. So we need to subtract this from the diagonal. 1 minus 5 is negative 4, 3, 4, and 2 minus 5 is negative 3. When we write our equation, I'm going to have negative 4x1 plus 3x2 equal to 0. Solving for x1 is going to give me 3/4 x2. When we write our vector, we write the equation for x1, and then x2 is a free variable. We can factor out an x2. So any multiple of this is fine, and we tend to not like fractions, so I'm going to go ahead and multiply this through by 4 to get the vector 3, 4. And I'm going to go ahead and write that up here so that we can keep track of it. Now I'm going to do lambda equal to negative 2. So I have 1 minus negative 2 is 3, 3, 4, and 2 minus negative 2 is 4. When I write my equation, I have 3x1 plus 3x2 equal to 0. And solving this gives me x1 equal to minus x2. So when I write my vector, I have an equation for x1, and x2 is a free variable. We factor out our free variable, and we get negative 1, 1. So that's my eigenvector for negative 2, would be negative 1, 1. Now that I have my eigenvalues and eigenvectors, I can start to diagonalize. So P will be the matrix containing my eigenvectors as columns. So 3, 4, negative 1, 1. D is a diagonal matrix, meaning everything not on the diagonal is a 0. And the diagonal will come from the eigenvalues, 5 and negative 2. In here, order of P does not matter. So if I want to, I can write this vector in the first column as negative 1, 1, and 3, 4 in the second column. However, the order for D matters. The fact that I used a -1, 1 here corresponds to an eigenvalue of -2, so that should be the first entry in this diagonal matrix. 3, 4 corresponded to lambda equal to 5, so that will be the second entry. So it doesn't matter which order you put your eigenvectors in as long as the eigenvalues are put in the same order. Let's look at this one here. Once again, we're going to start by subtracting lambda from the diagonal. So 2 minus lambda, -1, 1, and 4 minus lambda. And then we take the determinant. 2 minus lambda times 4 minus lambda minus -1. And we need to know when this is equal to 0. This gives me lambda squared minus 6 lambda plus 9 once I simplify it. And this factors into lambda minus 3, lambda minus 3. So we have one eigenvalue here, which is lambda equal to 3. When I try to use this as my eigenvalue, 2 minus 3 is -1. -1, 1, and 1 minus 3, or 4 minus 3 is 1. This gives me the equation x1 plus x2 equal to 0, or x1 equal to minus x2. So I have a -x2 and x2. Factoring out the x2 gives me a -1, 1, so this would be my eigenvector. And you'll notice here we only have one eigenvector and one eigenvalue. So when I try to make my matrix P, I have the first column but not the second one. So we don't know what this is. And in fact, in this case, this is not possible. So it's not always possible to diagonalize a matrix. We need the same number of eigenvectors as we have columns in the original matrix.